So a while ago we talked about solubility and how not all ionic compounds are soluble. And we had a list of rules, but we didn't really talk about how soluble anything was. And there were some that we said were slightly soluble, meaning they dissolve a little bit. Well, the dissolution or dissolving of an ionic compound is an equilibrium process. And so we can apply the idea of an equilibrium constant to the reaction or the change of something dissolving. So instead of calling it an equilibrium constant, we call it a solubility product constant, KSP. It's the equilibrium expression for an equation that represents the dissolving in an ionic compound. So it's got a special name. It follows the same pattern as the equilibrium expression. So we need to remember that solids are omitted from the equilibrium expression. And what we see is if we have a large KSP, we've got a compound that's very soluble, and a small KSP means the compound is not very soluble. So here's an example. First, what you need to do is you need to write an equation, a chemical equation, showing the compound dissolving. So here's barium sulfate. It's a solid, and we'll show it in equilibrium with the two ions that are present. Now barium sulfate, when we divide it up, we've got barium 2 plus ion and sulfate 2 minus ion. And so then the KSP, the solubility product constant, is the concentrations of the products multiplied, divided by the concentration of the reactant. But the concentration of the reactant doesn't change because it's a solid, and we don't include solids. So these end up not being fractions. They are just the ions. KSP value is something that you look up in a table. Let's go back to that just a minute. That's not what I meant to do. So if KSP is a big number, that means we're going to have relatively high concentrations of barium ion and sulfate ion, right? Because there's nothing for it to be divided by. And if KSP is small, then I'm going to have small concentration. So large KSP, soluble compound, small KSP, not very soluble compound. And when we look at these solubility product constants, like barium sulfate, 1.07 times 10 to the minus 10. That's a small number. Barium sulfate does not dissolve in water very much at all. Just a little teeny tiny bit. Can you pick out one that is soluble? Or one, which one is the most soluble? None of them are very soluble in this list. Which one's the most soluble? Probably this one. Oops. Here we've got calcium sulfate is 7 times 10 to the minus 5. And lead chloride is 1 times 10 to the minus 5. So those are pretty similar. So KSPs, you look them up in a table or they're given to you in the problem. You don't memorize these either. Let's write KSP expressions for each of these ionic compounds. The first thing we have to do is write the equation, chemical equation. So what we do is we start with the compound as a solid. And that's in equilibrium with the two ions. What are the two ions in silver iodide? Ag plus and I minus. There's one silver ion and one iodide ion because these subscripts are ones. We just didn't write them. So then this is a solid. We don't include that in the KSP. So KSP equals the silver ion concentration times the iodide ion concentration. What about calcium hydroxide? What's the chemical equation? What are the two ions? Calcium ion. Calcium has a 2+ charge. And then we have hydroxide. We have 2 hydroxides. This subscript here, there's 2 of them. So when this comes apart into ions, we get 1 calcium ion and 2 hydroxide ions. And it's really important to have that 2 in there because that becomes the exponent in the KSP expression. So then KSP is the calcium ion concentration times the hydroxide ion concentration squared. The charges have nothing to do with these exponents. So that's the charge on the ion. This exponent comes from the coefficient in front of the ion formula. Any questions? We can use KSP to find molar solubility. What do we mean by molar solubility? Well, what do we mean by solubility? Solubility is the amount of compound that dissolves in a certain amount of liquid. Well, it's going to depend on what that certain amount of liquid is. So molar solubility is a little more specific. It's the number of moles of compound that will dissolve in 1 liter of solvent. So moles per liter, it's related to that concentration. It's the number of moles per liter of solution. Well, here we have silver chloride, and when it dissolves, lovely train. Yeah, same to you. So we get silver ion. And chloride ion. And KSP is this number. This is a small number, 10 to the minus 10. How can we figure out what the molar solubility of silver chloride is? How many moles of it will dissolve in 1 liter of solution? Well, we go about it by finding these concentrations. If 1 mole of silver chloride dissolves, how many moles of silver ions do I get? 1. And I get 1 mole of chloride ions, right? How many moles per liter would be equal to the concentration of this that I end up with? So what I'm going to do is I'm going to write the expression. I'm not going to change the page, and I just did. KSP equals, will be the silver ion concentration times the chloride ion concentration. And we're just going to say S equals the moles of silver chloride that dissolve per liter. And that happens to equal the concentration of the silver ion, which equals the concentration of the chloride ion. Because if 1 mole of this dissolves, I get 1 mole of that and 1 mole of this. This is like a pair of shoes. There's the silver ion is the left shoe and the chloride ion is the right shoe. If I have 5 zillion pairs of shoes and they come apart, how many left shoes do I have? The number was 5 zillion. I have 5 zillion of these. Is it possible to have a different number of chlorides when they came in pairs? No. Those two have to be equal. Does that make sense? Because this is a diatomic compound. binary. There's two elements, there's two atoms or ions in it, and when they come apart, I get one of each. And so they have to be equal. So I'm going to say that the solubility is equal to the concentration of those ions, and they are equal to each other. What that means is I can plug S in for Ag plus and for Cl minus. And so what I end up with is KSP equals S squared. Then how do I find out what S is? I take the square root of both of them. So S is the square root of the KSP, and they gave me the KSP. 1.77 times 10 to the minus 10, square root of that. 1.77 EE 10 minus square root 1.33 times 10 to the minus fifth. What are the units on that? Moles per liter. Because that's what all the concentrations in a KSP are, in any equilibrium constant expression. So what this is telling me is that when I put silver chloride in water, mix it up, let it dissolve as much as it's going to dissolve, 1.33 times 10 to the minus 5 moles of it will dissolve for every liter of solution that I have. From that 1.33 times 10 to the minus 5 moles, I'm going to get equal amounts of silver and chloride, and they're going to equal the number of moles that dissolved. Yes?
So the KSP, would it always be the square root of the S? Or is it just for this problem?
This works for this sort of problem where I have one cation and one anion. And that's all it will work for. But the good news is that's all we're going to do in Chem 3A. Because when you get to things that are more complicated, it gets messy. So we don't need to go there, so we're not going to. We'll leave that up to Chem 1B.
So how about the other problems where we're taking the square root with the coefficient? So if there's a larger coefficient than 2, we're going to be taking the cube root of it?
You could conceivably end up taking a cube root, yes.
Yeah, because we're going to probably, I'm sure they're not all going to be 2 as the coefficient, right? In the molecular
Right. Yeah. They're not going to do anything too crazy because some people's calculators can't do crazy roots.
So like when we have a different number than 2, how will we do the square root on our calculator?
I don't know that you'll come across one like that. I'm just trying to look at my calculator. My calculator does have a button that allows me to take different roots. It's on the y to the x button. It's the x root of y. And so that's how you would do anything besides a square root. But I don't think that's going to come up, certainly on an exam. It won't. Any other questions? Yes?
So just to be clear,
Mm-hmm.
all you're doing is finding what S is,
Mm-hmm.
and by doing that, you just take the reactant?
We're going to take the products times each other, their concentrations, divided by the reactants. That's how we do an equilibrium expression. But here, this is a solid. And we leave solids and liquids out because their concentrations can't change. So for KSP, it's always just going to be the products. And that equals KSP. For other types of equilibria, these two things do not have to be equal. Okay, they don't. But this is, we're taking this solid and dissolving it in water and seeing what concentration of ions forms. And because of how that is done, they will have to be equal for a 1-to-1 ion, where the subscripts are 1. You have to have equal numbers of cations and anions.
So if it wasn't equal, we would
Right,
Okay.
yeah. But we're not going to go there. Yeah. That ends up being a little more algebra than we want to deal with.
So S would always equal the reactants or whatever is.
For an ionic compound where it has a ratio of 1 to 1, the molar solubility will always be the square root of the KSP.
Okay. How did you get S squared? That's where I got lost. When you said S squared.
Okay. So what I did, let me change to a slightly different color here. So what I said was that this is equal to S. So that's S. And this is equal to S. So now I've got S times S, which is S squared. Does that help?
Is that always the case? They're both going to just be S?
Yes, for a 1-to-1 ratio ionic compound. Yeah. And calculating solubilities, that's what we're going to do. Now, if I gave you the concentrations, I could ask you to calculate a KSP for a more complicated equation, but I wouldn't ask you to find S. Question?
Obviously, in the case of a compound like acetate,
Mm-hmm.
would it be Q? S times S.
Well, it depends. So you guys seem to be real curious about this, so let's look at it. If it was something like sodium acetate, solid dissolving in water, what are the two ions that forms?
Chloride, sodium.
Chloride? Acetate, right? This is a 1-to-1 ratio. There's one of these to one of those. What if we had something like calcium chloride? Well, that's going to form calcium 2 plus and 2 chlorides. It's not 1-to-1. And so then, the molar solubility, if I have 1 mole of this, I'm going to get 1 mole of that and 2 moles of this. So this is going to be equal to S. Because that's going to equal the number of moles of that dissolved. And then how is this related? Cl minus, we're gonna get twice as many, right? So what's the actual chloride concentration? The chloride concentration will equal 2 times S. It's supposed to be capital S. Looks like a S looking in the mirror. And so then KSP equals calcium ion concentration times the chloride ion concentration squared. So then we get S times 2S squared, and we get 4S cubed is equal to KSP. So then you end up with S, wrote way too big, S being equal to KSP divided by 4 and the cube root of that. Right? So it's not horrendously hard, but you guys have other things to learn too. So for the curious, that's how it works if it's more complicated. There could be a homework question that does something like that, but I promise you I won't do it on an exam.
What about like on the finals, like on the state problem?
I will look. I'll look, but I'm pretty sure they won't do that. Did that answer your question?
Yes.
Good. Okay, so let me make sure I didn't miss anything. Okay, calculate the molar solubility of calcium sulfate. We need a number to do this. We can't just start calculating without any numbers. What number do we need? We need KSP. And we're going to get that by looking in the table. So we're just going to trot back here and find KSP for calcium sulfate. 7.10 times 10 to the minus 5. KSP equals 7.10 times 10 to the minus 5. So I looked it up. Now we need to write the chemical equation for calcium sulfate dissolving. We're going to get calcium ion and sulfate ion. Is that balanced? It is. So KSP equals the calcium ion concentration times the sulfate ion concentration. The calcium ion concentration will be equal to the sulfate ion concentration, which will be equal to S. So this then equals S times S, which is S squared. S ends up being the square root of KSP. 7.10 times 10 to the minus 10 square root. .66 times 10 to the minus 5. Now, in terms of significant figures, it's usually going to just, whatever numbers you're starting with, here it's 3, I'm going to end up with 3. We're not going to worry about craziness with sig figs. We still care about it, but just go with whatever you started with. Any questions? Yes? Okay, let me see how you did it on your calculator. Okay, so I screwed up. This is a -5, and I wrote -10, and that messes things up. -5. So then this is like completely wrong. But it does demonstrate why it's good to show your work, because then you can go back and see what you did that was incorrect. So 8.43 times 10 to the minus 3rd. 8.43 times 10 to the minus 3rd moles per liter. Thank you for asking. Any other questions?